Welcome to the physics class for October the 26th. Today is going to just be a review day. I plan to spend pretty much the whole day just going over the practice test and or any other questions that you have. The answers to the practice test have been posted on Canvas. I trust that you've already downloaded those and looked at those. So if you find that you don't need to talk about those, but you have other questions, I'm definitely okay with that. Before I get into that, let's talk a little bit about the test that's going to be coming up. So you all understand next time we meet will be the test. And also, hopefully you understand that I am going to do it differently this time than I did last time. I'm going to do it more like what I'm being told other teachers are doing. What I'm hearing from students and also from the other teachers is that the way they've been doing tests in other classes is they have you log on to Zoom with your cameras turned on so the teacher can monitor you while you're taking the test. Excuse me. So I'm going to give that a try and see if I like that better than the other way. So on Wednesday, or if you're watching the recording and you're in the B-Day class, for the B-Day class, it'll be Thursday. But for you A-Day classers, on Wednesday, log into Zoom, turn on your camera, and then I'll unlock the test on Canvas, and then you can get started on Canvas, but keep your Zoom camera on so I can monitor you. Now, there's going to be two types of questions on the test. The first bunch of questions are all going to be worth 2 points each. They're going to be multiple choice or similar type, fill in the blank, whatever, where you don't have to type in a numeric answer. You can just choose. Those will be worth 2 points each, and those you either get right or you get wrong. There's no partial credit to be had on those. And then the last bunch of questions will be 5-point questions, and those will be ones where you need to do a calculation and you need to type in a final answer. And those are ones that I will give you extra credit, or I will give you partial credit on. If you can email me your work so that I see that you basically knew what you're doing and just made a silly mistake. Now, when you submit the test, Canvas will grade it right on the spot. And I'll have it set so that you can go in and you can see which problems you missed. So don't email me all of the problems. Only email me the work for the problems that Canvas tells you got wrong. And make sure you do it by midnight on the day of the test, because I won't accept them after that. Last time around, there were a fair number of you who could have gotten partial credit, probably, but I couldn't be sure because, your answer was wrong, and I had to guess at what you did wrong. And I can't give you partial credit based on a guess. You need to send me your work. And if I can see that it was just a silly blunder, the kind that I frequently make, I'll be generous with the partial credit, but only if you email me your work. Okay, let's see. Also, regarding quiz retakes, you may recall that last week I told you that I wanted to change the way that quiz retakes worked, because there were too many people who were just blowing off the quiz and then doing it later because there was no penalty, right? And so, I can't complain. That's the way I set it up. It was my fault for setting it up that way. So several of you emailed me your comments saying that you liked the fact that you could come back in and retake the test later, and you hoped that I didn't completely do away with that. So you made some good points. I heard what you said. So I'm going to compromise. What I'm going to do is I'm going to allow you to retake quizzes, as many as you need, but with a slight penalty, only a slight one. So if you get a perfect score before the deadline, then great, you can get 10 out of 10. But if you don't take the quiz before the deadline, or if you don't get a perfect score before the deadline, then after the deadline has passed, then I will not allow you to get a 10 anymore, but you could get a 9. And so the best you could possibly get would be a 9. And in order to get that 9, you'd have to get a perfect score. Okay, so let's see, any questions about any of that?
So you'd have to get the 10 on the very first try, basically.
Uh, yeah, that's something I've wrestled with. Up until now, some of the quizzes I've only given you one shot at prior to the deadline. After the deadline, then I unlocked it and you take as many as you want. But some of them I only gave you one shot at it before the deadline, whereas others of them, I gave you 2 shots before the deadline. So I'm going to kind of do the same thing now. Depending on the circumstances, I might give you 1 shot or I might give you 2 shots before the deadline. So if if I give you 2 shots, then great, you can hopefully get a 10. But once the deadline passes, then the best you can hope for is a 9. Okay. One other thing before we start into the practice test is I was looking over your homework from 5C, and I noticed there was one problem that quite a few people got wrong. And so I figured I'd better talk about it. It was problem number 57 in chapter 5, where they're asking about the wheels, the tires on your car. And basically they're asking, if you get fatter tires, will that give you better traction, like meaning better friction? And a fairly large number of you said yes, using fatter tires will give you more grip on the road. Actually, that's not the way it works. Here, tell you what, let's open up a whiteboard and let's talk about this, because this is something that's important for you to understand. Let's say that I've got some box sitting on the floor and I'm pushing on the box, and so the box is pushing back. So this is the force of me pushing, and this is the force of friction. And so I want to know how much friction force do I have to overcome in order to push this box. So you guys know that the friction force is defined as mu times the normal force. Now, if it's kinetic, then it's an equal sign. If it's static, then it's a less than or equal sign. But in either case, the things that go into the equation are mu and the normal force. And what is the normal force? Well, if you're on flat ground like this, the normal force is mg. If you were on an incline, then the normal force would be mg cosine theta. But if you look at this equation, where does the surface area come into the equation? Answer, it doesn't. So it doesn't matter if the box that I'm pushing is a tall, skinny box, or maybe it's a short, fat box. All that matters is what is the mass of the box. So if the mass of this tall, skinny box is the same as the mass of that like pizza box, the friction is going to be the same, even though the surface area here is clearly very different, because surface area doesn't come into the equation. Now, people wonder about that. They say, well, hang on a second here. What is it that causes friction? Well, it's surface roughness, right? So if we've got a rough surface, okay, then if we have more area in contact with that rough surface, it makes sense that we should have more friction. And you are right in thinking that. But at the same time, the force that's squeezing these two surfaces together, that force is going to be spread out over a larger area.
Yeah, the pressure is
if it's
higher,
spread
right?
out. I'm sorry?
The pressure is higher, correct?
Yeah, in this case over here on the left side, the pressure is higher, right? Okay, so on the pizza box case, the force is spread out over a bigger area, and so that leads to having less friction. So what happens is you got the one thing that says it increases the friction if you get more area, and the other thing says you decrease the friction if there's more area. The two of them cancel each other out. So in the end, it matters. It turns out that the amount of surface area doesn't matter. Okay. Now, some of you are going to say, well, now, wait a minute, Mr. Hendricks, because I enjoy watching drag races, either in person or on TV. And when I look at the tires on those drag race cars, those tires are really fat. Okay, they wouldn't have those fat tires unless they had a reason. So it must be because fat tires grip the road better than skinny tires do. Well, not quite. That's not the way it works. If you want to increase the friction on your car, on your tires, what you want to do is you want to go to a softer rubber. Increasing the surface area doesn't affect the friction, but going to a softer rubber does. Okay, so if you were to look at the rubber on those special tires that drag racers use, what you'll find is that it's a softer rubber that has a higher coefficient of friction. So then you say, but then Mr. Hendricks, why do they make the tires so wide? Because the softer rubber wears down a whole lot faster. So if they made the tires the normal width, then what would happen is they would wear out their tires really quickly, like maybe even in one race. Their tires might not even last for one race. By making the tires wider, then it spreads out the wear and tear so that the tires will last longer. Okay, so any questions about that? Oh, I see. So Calvin has said, if you lower the tire pressure, that would have a better grip. It's complicated. If you're on a road, lowering the tire pressures doesn't do anything for you. But if you're off-road, like, I don't know, Calvin, I don't know if you're into Jeeping, but I really like riding around in my Jeep off-road, and I lower the tire pressure in my Jeep when I go off-road on really rough surfaces. And and the reason for that is because then the tire can conform to the roughness on the road. So say you're going over some big rock or something like that. If your tires are softer, then the tire can conform so that way it's less likely to slip off the rock. You have that's the reason there. And if you were on a flat road, lowering your tire pressure would do nothing for you in terms of increasing your grip, but on a rough road it would. Okay, let's start into the practice test then. So I'm going to share my screen with you. And then let's scroll up to the top here. The first couple of problems I do not expect I'm going to spend very much time on. I'm just going to hit them really briefly. I'm assuming that these are the easy ones. I hope you agree. Just a couple things I want to point out. So terminal velocity. It's very important that you understand how terminal velocity works. A lot of people think that when you step out of the airplane or the helicopter, okay, and then you start, so at that brief instant, if we do a free body diagram on you, the only force that's acting on you is the force of gravity pulling you down. This is assuming you've stepped out of a helicopter. If you step out of an airplane, then you've got some vertical motion, so that confuses, or you got some horizontal motion. That confuses things. So let's not deal with that. Why does my eraser not want to erase? There we go. Okay, so if you were to step out of a helicopter, at first the only force acting on you is mg. So yeah, you're definitely going to start accelerating downward. And then as you start moving downward, then you start getting some air resistance force on you. And then as you go, it gets bigger and bigger and bigger until you reach the point where the air resistance force is equal to the force of gravity. Now, I've had several students tell me, oh, does that mean that you stop falling because the forces are equal? No, it means that you stop accelerating. You're still falling, you're just not accelerating anymore. Okay, so you've reached the maximum velocity that you're going to get. And so that's what we call terminal velocity. So yeah, Calvin, you are exactly right. The air resistance equals the weight of the person. Yeah, that's exactly what happens. Okay, so problem number one is one that you should be able to do without a calculator. And back in the days before coronavirus, when I had my test divided into two parts like this, I told students that on the no calculator part of the test, whenever you needed to know what G was, instead of using 9.8, I said, just call it 10. That way it makes it easy to do in your head without a calculator. But on the yes calculator part, then they had to use the real value, which is 9.8. So for you guys, Oh, I meant to say this before and I forgot. So when you guys take the test, there will only be one part to it. And you will be allowed to use your calculator on the entire part. And you can use all of your notes. And in fact, if you want to open up the book and flip through the book, you're welcome to do that. In fact, even if you want to Google something, that is not cheating, but it is not a good idea. And the reason it's not is because I'm designing the test so that a typical student should be able to finish it in 80 minutes without, and that's if they don't look in the book. If you have to take time to look in the book or Google something, that's using up precious time. And what you're going to find is that you're going to run out of time on the test if you have to do that. So remember we talked about cheat sheets and why you should make up a cheat sheet? Yeah. Not only is everything that I said last week about cheat sheets valid, and you know how the act of creating a cheat sheet is the best thing you can do to summarize in your mind what's important and what's not. But also, if you have it on your cheat sheet, then you can just look on there and get it right away. You don't have to waste precious time looking in the book. Okay, so even though you are allowed to look in the book and even though you're allowed to Google stuff, I don't recommend you do it. Okay, because you will run out of time if you try that. Okay, back to the practice test. All right, so question number 2 is just definitions. So you should hopefully have no trouble with that. Question number 3, the difference between static friction and kinetic. And basically what I wanted to get after here was I wanted to make sure you understand why it is that we have a less than or equal sign. When we're doing static friction, why isn't an equal sign like it is for kinetic? Okay, and the reason for that is because if I'm doing static friction, okay, so if I have an object on the table and I'm pushing on the object, the amount of friction that it pushes back with is not just one number. It will match whatever I'm doing. If I push with 1 Newton, it'll push back with 1. If I push with 2, it'll push back with 2. It will adjust to match whatever I'm doing. And so I can't just say an equal sign because it is going to vary, but it'll only vary up to a certain point. Once I exceed the breaking point, okay, then it can't adjust anymore. And so then it starts sliding. But if I have a case where something is sliding already, okay, then there is one number and only one number that is the amount of friction force that it will resist with. It's mu times whatever the normal force is. It doesn't matter if I'm pushing harder than that or if I'm pushing less than that. It is one number and it will always be that one number when it's sliding. Okay, but when it's static, okay, then it's a little bit different situation. So make sure you understand that. There might be a question on the test designed to see if you really understand that. Okay, question number 4, free body diagrams. You guys should be really good on free body diagrams by now. Question number 5, we've got somebody pushing a crate. So if we want to know how hard they have to push in order to start the crate moving, what we do is we take the equation, or actually it's not the equation, we take the expression F friction is less than or equal to mu s times the normal force. And what we do is we take that and we make it be an equal sign with the understanding that if this is an equal sign, then this value that we calculate here is not just any old FF, it's FF max, okay? Which is what we're after in this particular case. So, okay, next, Newton's laws. All right, so remember, the practice test here was written back in the days before coronavirus, where the first part of the test, you were required to do it without using any notes, not even with your one-page cheat sheet. So there are some things that you do need to know from memory. And Newton's laws, you need to know what is his first law, what's his second law, what's his third law. You need to know that from memory without having to rely on a cheat sheet there. Question number 7. Taking a funky vector and breaking it up into its components. I'm really hoping that by now you guys are super experts at that. This should be something that you shouldn't even have to think about. If you've got a funky vector here, the hypotenuse is, okay, All right, so in this case, the hypotenuse is 92. And so if we want the eastward component, that's going to be, it'll tell you what, let me make this picture a little bigger. So, okay, so here is the vector. Okay, so that breaks up into two components. There's a northward component, there's an eastward component. So you guys should have done these so many by now that you should know that this component here is going to equal whatever the hypotenuse is times the sine. Okay, so 92 times the sine of theta. Okay, you shouldn't even have to think about that by now. Should be second nature. And if it's not, then that tells me you need to do some more homework problems. All right, so a few more definition terms. Shouldn't have to worry about those. A couple of really easy Newton's second law questions. I'm hoping that you guys agree they're easy, so I don't want to take the time to do those. Question number 12 is one that I do think we should talk about. This is one that this is a question that I have put on tests previously, and I was dismayed at how many people got it wrong. Okay, so I don't want you guys to make this mistake. Now, some of you are going to say this is a trick question. I disagree. I don't think it's a trick. So what we have is we have an elevator moving upward at a constant speed of 2 meters per second. So if it's a constant speed, we don't care what that speed is. We don't care whether it's 2 meters per second or 20 meters per second or 2,000 meters per second. If it's a constant speed, then the value of that speed is irrelevant. The important thing is that the acceleration equals 0. So if the acceleration is equal to 0, then it's the same as if it's not moving at all. So then the upward force and the downward force will be equal to each other. Okay. Now, some students say, but Mr. Hendricks, if you gave us that 2, if you gave us that number 2, then we thought that you wanted us to use that somewhere in the equations. Well, no, I gave it to you as a red herring. I'm sure that many of you guys have taken the ACT, the college entrance exam. And those of you that haven't, you're going to be taking it real soon. What you're going to find is that a lot of the ACT questions are basically, they give you some paragraph that you have to read that is just filled with information, most of which is irrelevant to the question that they're going to ask at the end of the paragraph. And what they're testing is they want to see if you can sort through all of this information and figure out what's important and what's not. Okay, that's what they're testing. And so I throw in a couple tests like that on my test too, to see if you can figure out of all this flood of information that I gave you, in this case, flood is the wrong word. It's just, I only gave you one extra number is all I did. Okay, so that's not a flood of information, but it's enough that, people think, well, hey, he gave us the number, therefore we must use it somewhere in an equation. Bzz, no, not the way it works. Okay, now question number 13 at first glance looks like it's the exact same question as number 12. But it's not, because that number 2 that I just told you you didn't need back before. Okay, well now you do, because this time that 2, it's not the velocity of the elevator anymore. That 2 is the rate of acceleration. Okay, so this elevator is accelerating upward at a rate of 2 meters per second. So yeah, that 2 now all of a sudden becomes very relevant. So if the elevator is accelerating upward, then my picture here is not really the best picture, because if it's accelerating upwards, then the upward force must be greater than the downward force, because otherwise it wouldn't be accelerating upward. So really, this arrow up, the upper arrow, it should be longer, because otherwise it wouldn't be accelerating upwards. Okay, so if we do sigma F equals ma, then that turns into the upward force minus the downward force equals ma. And so then we can then just bring this over on the other side. So this equation right here is basically the elevator equation. And it applies equally well if the elevator is not moving. If the elevator is not moving, then the acceleration is 0, so Fn just equals mg. Even if the elevator is moving, if it's moving at a constant speed, then the acceleration is 0 and Fn equals mg, just the same as if it wasn't moving. But if it's accelerating, which it is in problem number 13, okay, so then we got to do the full thing here. And so we do this plus this, and we get an answer of 590 newtons. Okay. Now, we should always, always, always think about significant figures. If you look at our input numbers, one of those input numbers only has one sig fig in it. So that means we are not allowed 2 sig figs in our final answer. That means we need to round it off to 600. So be careful about that. I don't want you guys getting these wrong because of silly mistakes like this. Now, if I were to put a problem like this on the test, it would probably be a 5-point problem. And so if you type in 590 as your answer, Canvas is going to mark it wrong. But if you then show me your work and I can see, oh, okay, you just forgot to round off, I can still give you 4 out of 5 points. Okay. But every year I always have some students where this is the answer they get on their calculator. And when they round off for some unfathomable reason, instead of rounding up, they round down. And so they put 500 on as their answer. And I mean, that's definitely the wrong answer. So I sit there and I wonder, did they do the physics right and just round wrong? Is that the problem? Or did they do the physics wrong? And I don't know. I mean, if you don't show your work, I have no way of knowing. And so if all you put down is the answer, I would have to give you 0 points. But if you show me the work, then maybe I'd give you 4 out of the 5 points. Okay, so show your work and email it to me before midnight on the day of the test. But if Canvas tells you your answer is right, then please don't email me those. Okay, just only email me the ones that Canvas tells you got wrong. Okay, how are we doing here for questions? Am I going too fast, too slow? Are you about right? Okay. Yeah, Sam is saying, hey, kids, stop being annoying. Okay. All right. So question number 14. This is kind of a Newton's third law type question. So if I want a free body diagram of the object of the block that's in the middle there, okay. So first off, you have to recognize that if it's anywhere near a planet, you're going to have gravity acting on it. Second off, you have to realize that if there's a rope underneath here, that rope is going to be pulling on it. So we're going to have a force for that. And then third is if there's a rope on top there, then that means that rope's going to be pulling on it. So we're going to have a force for that. So I need to see all 3 of those arrows there on the free body diagram. Yeah, not much more to say about that. Okay, so I'm thinking I can skip over that. Question number 15 is a good one, in that this is a multi-step problem. And you guys need to be good at solving multi-step problems. Remember the speech I gave you the other day where I said, my number 1 goal for you guys is not for you to learn physics. Although obviously I want you to learn physics, it's not my number 1 goal. My number 1 goal is for you guys to learn how to solve difficult problems where you have to approach them in steps. So in this case right here, all right, so we want to know what is the force that's acting on this object. So we say, okay, well, how would we calculate the force? And you'd say, well, it doesn't look like we've got enough information to calculate the force. So then you have to say, okay, all right, but if I knew the acceleration, then could I calculate the force? And you say, yeah, but rats, we don't know the acceleration. So then you say, okay, so what would I have to do in order to find out the acceleration? And so you break it up into steps like that. So this is something you guys need to be really, really good at. Okay, so in this case, we say, all right, so force is the ultimate goal, but we can't know that until we first know the acceleration. So how could we find out the acceleration? So if we read up here, we find out that, hey, this looks like a Dr. Seuss problem. I mean, this is all the given information here. And so I'm thinking, yeah, we've got enough information to find the acceleration. So we say, what equation has an A in it but doesn't have a T in it? Well, there's only one. It's this one. So using the information here, we can find out what the acceleration is. Once we know what the acceleration is, then we can stick it into this equation, and then we can get the force. So multi-step problem. I guarantee there will be problems on the test like that, where you're going to have to break it up into pieces. And before you can get the final answer, you're going to have to figure out how to get the intermediate answer. Guarantee there will be problems like that. Okay. Number 16, a vector problem. All right. So before I talk about how to do number 16, let's just step back for a minute and let's just talk about vector addition, because I know from past experience that even after doing all these problems, still there are students that are still a little bit iffy on how to do vector problems. So what I'm going to do here is I'm going to share a presentation with you. All right. So let's suppose that we've got a box and there are 4 different forces acting on this box. I'm sorry, I can't count. I can do advanced calculus, but I can't count to 3, can I? Okay, so there are 3 forces all acting on this box at the same time. And so we want to know what is the net force on this box. Or maybe they're not force vectors. Maybe they're velocity vectors. Maybe what we do is we have a boat going through the water, where this vector right here is what the velocity of the boat would be if the water wasn't moving. But the water is moving, so we've got current here. And also we've got the wind blowing on the boat. So the wind is blowing the boat, we've got some what we call leeway this way. So we want to know what is the actual velocity of the boat going to be. So it doesn't matter if these are force vectors or velocity vectors. They all work the same. So when you have to add vectors, students get all nervous and all freaked out. Look over here. You see this little poster I made up here? You've probably seen before, keep calm and carry on is a very common phrase. So I took that and I modified it. Keep calm and defuncify the vectors, and everything will work out. But also you need to remember, how is it that sailors add vectors? Because if you don't add vectors the sailor way, then it's not going to work out for you. So let's see, how is it that sailors add vectors? So what you see here, this represents what's actually happening to the box. All of the forces are acting on the box. But when we want to add the vectors, we do not portray them this way. Let's pull these vectors off to the side here. So let's get him over here, and him over here, and him over here. Okay, so what we want to do is we want to add the vectors one at a time, and it doesn't matter what order we do them in. Okay, so tell you what, let's take this guy and let's put him there first, right? So now we want to bring in the second vector. So even though the second vector is technically acting at that place right there, that's not where we put it. We put it up here so that the tail of the second vector starts where the head of the first vector ended. And now we have to add our third vector. So we do that. And again, even though technically the third vector is acting down here, we bring it up here. Okay, so the tail of the third vector, it starts where the second vector ended. All right, so now we have a resultant vector. So the resultant vector is the vector that starts where they started and ends where they ended and doesn't care what happened in between. This is sigma f. Or if it's a velocity vector, it would be sigma v. Whatever the vectors are, this is how you do it. Okay, and it doesn't matter what order I do it in. Okay, let's suppose that instead of doing it in the order that we just did, let's say that we take this vector first, and then this vector next, and then, hey, look at that. They end up in the same place. Or what if we do this vector first, and then this vector second, and then this vector third? Hey, look at that. They end up in the same place. Okay, so the order does not matter. All right, so how do we do this? Well, we take each vector one at a time. What we do is let's call this guy the A vector. Let's call this guy the B vector. Let's call this guy the C vector. And so the A vector, if we defuncify him, we come to a vector that looks like that and like that. So this vector here, I'm going to call that AX. And this vector here, I'm going to call this AY. And you know how to get it because you know that AX is just going to equal A times the cosine of theta. And you know that AY is going to equal A times the sine of theta. Okay, so this is a number that you can calculate. This is a number that you can calculate. All right, so then we don't need the funky guy anymore. What do we do with the B vector here? Okay, well, we break him up to a vector that looks like that and like that. And so this guy, I'm going to call him BX. And how would I get a number for him? Well, he would be B times the cosine of theta. Okay. This guy right here, we could call him BY. How do I get a number for him? B times the sine of theta. All right. Now we don't need our B vector anymore because we replaced him with his components. All right. Now, how about C? Same thing. This guy right here, I'm going to call that CY. That's going to be C times the cosine of theta. Let me fix that here. Okay, it's going to be C times the cosine of theta. This guy here, going to CX. That's going to be C times the sine of theta. Bingo, don't need him anymore. Okay. So yeah, it's a little bit tedious perhaps, but it's not difficult. So now what I do is I come over here and I say, okay, if I add up all the forces that are in the x direction, okay, I'm going to get AX plus BX minus CY, because why he's going in the minus direction. Okay, so that's going to give me some number. And I do the same thing in the y direction, sigma F in the y direction. Well, that's going to be negative AY, because that's going in the downward direction, positive BY, and positive CY. Okay, so this then equals some number. All right, so now I've got these two numbers, and those are now the components of my final vector. So my final vector then is going to have a component that looks like this, which is going to be sigma Fx. And it's going to have a component that looks like this, which is going to be sigma Fy. Okay, and so this is a number that I can calculate. This is a number that I can calculate. Tell you what, let's move him over on the other side. Let's move him over here. That's sigma Fy, and that's some number I can calculate. And why did I move him over there? Because I wanted to have room so I could put my hypotenuse. So this is the resultant force. And a resultant force. So if I want to know the magnitude of this resultant force, all I have to do is take sigma Fx, sigma Fy, and then just Pythagorize them. Okay, put them in the Pythagorean theorem, right? And if I want to know this angle, well, I just take the inverse tangent of whatever this guy is divided by whatever this guy is. Okay, so you see this, so approach it the way that a sailor would approach it. I can't tell you how many times I've seen it where students, they take the one vector here, but let's just make it a two vector problem. Let's just get rid of this guy completely. Let's pretend it's a two vector problem. They draw the one vector here, they draw the other vector there, and then I say, okay, so where's the resultant vector? And they say the resultant vector is this vector right here. Bzzzt, no, it's not. Okay. Well, you have to do it the sailor way. You have to take this vector here and you have to move it up there. Okay, and your resultant vector is, oops, sorry, I need to turn on annotation before I do that. Okay. The resultant vector is this guy, not the other guy. Okay, so guys, keep that in mind. Every year, no matter how much I stress this, I always have people who make the same mistake when they're adding vectors. So you have got to be really, really good at adding vectors. So ho, ho, a pirate's life for me. Yes, Aurora, I agree. Pirates, they really had, They knew what they were doing. Okay, let's get back to the practice test. All right, so problem number 16, if you just approach it that way, okay, so I'm not going to go through everything, but let's take a minute to set it up. That's probably worthwhile. Okay, so we've got an airplane and the pilot thinks she's going straight south, but what she doesn't realize is that the wind is blowing off this way. So what the pilot is actually doing, what the airplane is actually doing is going over this way. So that's just a Pythagorean problem. That's really easy to get. And the angle there is just the inverse tangent. So that's really easy to get. The trickier one is problem number 17. Okay. So problem number 17 is the same plane as before. So the pilot now realizes that the airplane is being blown to the east. And so she knows in order to counter that, she has to point kind of southwest-ish. But she's so busy flying the airplane, she doesn't have time to work out the math to figure out what angle to point herself at. So she just guesses. She says, oh, let's try 34 degrees. Let's see if that works. Okay. So it's the same airspeed as before. So that means when we draw our vector here, it's still going to be 210 that way. And the wind is still blowing this way, 52. What she's hoping is that by picking this angle, she's hoping that the eastward or the westward component of her speed will equal the eastward component of the wind. And so what we need to do is we need to see, does that work out? So this side right here is going to be 210 times the sine of what it was the angle, 34, yeah, 34. Okay, and what we find is that angle does not equal 52, not by a long shot. What we find out is that she overshot it by quite a bit. Let's see, 210 times the sine of 34. Okay, so this component here works out to be 117. So the wind is only blowing to the east at 52. Her westward component is 117. So she definitely overshot it here. So when we add up all of the x velocity vectors, we got 117 to the west and only 50 to the east. So that leaves us with 65 to the west. So then what we get is at the net, this number here, this is sigma velocity in the x direction. This number here is sigma velocity in the y direction. And so if we want to know what is the airplane's real velocity, we just Pythagorize those two and we'll come up with 190. That's our answer for the magnitude. And then for the direction, all we have to do is just take the inverse tangent of 65 over 174 and we get 20 degrees west of south. Or if you wanted, you could also say that it's 70 degrees south of west. That would work too, because that angle right there is going to be the complement of that angle down there. Okay, so we good? I hate it when I'm doing all the talking and there's no feedback here. So give me a thumbs up or thumbs down, or give me a yes or a no in the chat box. Is this making sense? Can I move on to the next problem here? Okay. All right. I just got a private message saying that explanation really helped a lot. That's good. Okay. So let's move on to problem number 18 then. Okay, so problem number 18 is we've got some masses on a pulley. So I just got a private message from somebody asking if I'll post this recording. Do you guys want me to? So type in the chat box, yes, if you want me to post the recording, no, if you don't. Oh, yeah, yes, please, all in caps. Okay, all right. Okay, I'll post it then. But you still should take notes. Okay, so problem number 18 is just one of a great variety of pulley problems. So tell you what, before we do this one, let me open up a whiteboard And let's just look at all the different types of pulley problems that I might possibly give you. I guarantee that I will give you at least one of these pulley problems. Okay, so the simplest pulley problem is the one that you just saw. That's where you've got a ceiling. Here's the pulley. You got a mass right here. The rope comes up over, and then you got another mass over here. And your job is to find the acceleration. And maybe also the tension too, but the acceleration is the one that's most important to me. Okay, that's only one of the ways that I could do this. Another way I could do this is I could have a tabletop with a pulley over here, and then I have a mass right here, and this rope comes up over the pulley, and then I've got another mass right here, okay? So I could ask you to find the acceleration in this case, and the equations you need to use are going to be very different, and you need to be able to derive the equations. Oh, and by the way, if we've got this thing on a surface here, we might have some friction, or we might not, depends. So you better be able to do it both ways. You better be able to do it with friction and without friction. And there's also another case, we could do it like this, where I've got a ramp here, and here's the pulley, and here's my mass, and here's this rope coming over, okay? So here again, we might or might not have friction right here. So any one of these problems is fair game to put on the test. So you need to be able to do these types of problems. So problem number 19 is the simplest of them. So let's go ahead and do problem number 19. Okay. So you know how I said you're allowed to use your notes. So if you wanted to, you could just write down this equation and put it in your notes. And so if you get a problem like this, just use this equation and life is good. Now, I prefer you didn't do that. My preference is that you should be able to derive the equation. And in fact, you know what I do when I write the test, I might write it in such a way that I'll say that I don't care what number the acceleration is. I want to know, how did you get the acceleration? So I might ask you to derive it for me. Okay, so what you need to know is you need to know, look at this mass right here, and you got m2g going down and tension going up. So when you do sigma F equals ma, it's going to come out looking like this. Okay, and then you're going to say, okay, but over on the left side, we got m1g going down and tension going up. And when you put it into F equals ma, it comes out looking like this. Okay, and from this point on, now it's no longer a physics problem. Now it's just a math problem. If you want to solve it using the substitution method, hey, more power to you. I find that in this case, the elimination method is going to be the easiest way to do it. So that's why I've done it. But if you want to use substitution, you can. It'll work for you. Okay. So once we get it down to this equation right here, then it's just plug and chug. Just put in the numbers and out pops the answer, at least for the acceleration. And then once you have the acceleration, how do you then figure out the tension? Well, put it back into either one of these equations. It doesn't matter which equation you put it into. In this case, they're both pretty much equally equal levels of difficulty. I mean, generally you want to put it into one that's the easiest, but in this case, they both look equally easy. Okay. So this problem here is quite straightforward. What if I hadn't given you a problem like this? What if I had given you a problem like you see right here? Okay, how would you do that? Let's take a minute and do that. Let's do a problem like that. Okay, so here's the tabletop, here's the pulley. Here's a mass I'm going to call M1. Here's the rope coming up, going around it. Here's a mass I'm going to call M2. And let's say there is friction. Let's solve the more difficult case. So I want to know, what is the acceleration of these guys? Okay. Now every year I always have some students who try to take the equation from here. Okay. So this equation down here, they say, well, hey, this equation worked for this situation. Let's try to use that same equation in the other situation. Every year, I always have somebody who does that. And no, you can't do that because this is a different situation. That other equation we just came up with is not going to work. So we're going to have to derive the equation. So we're going to have gravity going down. So that's M1G going down. You got tension going up, okay? And these two are not going to be the same because the blocks are going to accelerate downward. So tell you what, let's do. Let's make sure that our tension force is going to be less than our mg force. All right, so then it's time to do sigma F equals ma. And so what goes under sigma F? Well, this guy and this guy both go under there. Okay, but one of them goes in with the plus sign, one goes in with a minus sign. We need to decide our plus direction. So if we know the object is going to accelerate downwards, then that's the logical way to do the plus direction. So that means that M1G is going to go in there with a positive sign, tension is going to go in with a minus sign, and that's going to equal M1A. This M here is M1. All right, so there's one of our equations, but only one. We need another equation. Where are we going to get it? Over here. And let me do that. I like my force arrows to be thick. Let me do that. Okay, so we're going to have M2G going down, the normal force going up, and friction opposing it. So if I sum up all my forces equals mass 2 times A, let's only do the forces in the x direction because that's the direction we know the thing's going to move, right? Okay. So, well, hey, it looks like we only have one force in the x direction. So that's the force of friction. But is it going to go in with a plus sign or a minus sign? So if the downward direction for this guy is positive, in order to be consistent, the plus direction for this guy has to be to the right. So that means our force of friction has to go in with a negative sign. Okay, so that has to equal M2A. All right, now what is the defining equation for force of friction? Well, whoops, where did that come from? Wow, never seen it do that to me before. Okay, so force of friction is mu times the normal force. And since we're on a flat surface, you can see the normal force is equal to mg. We don't have to worry about mg cos theta. So this is equal to mu times mg. So negative mu m2g equals m2a. So there we are, two equations, two unknowns. From this point on, it's no longer a physics problem. Now it's just a math problem, and you're good at math, right? Okay, so I'm going to stop there. But from this point on, it's just the same. I mean, as long as we know the numbers for M1 and M2, we can easily figure out what the tension is. But the important thing is that the equation we're going to get from this is not the same as the equation that we had here. Okay. This equation only applies for this situation. Okay, so unless I see any questions, I'm going to move on. I'm not seeing any, not hearing any. Okay, so I'm going to move on then. All right, so here we have the third of the possibilities. This is the pulley problem, but this time a guy is being pulled up the ramp. Okay, so if there's no friction, then this is the way to do it. And this is the equation to give us the acceleration, okay? But what if there is friction? So in problem number 19, there was not friction. But in problem number 20, it says this time there is friction, okay? So what I would recommend we do is let's go back here and for problem number 19, let's derive the equations, but let's assume that there is friction. Because if you have an equation that takes care of friction, it's very easy to use that exact same equation in the case where there isn't friction, because all you have to do is the term here that has mu in it, just let mu equal 0, because 0 times anything is 0. And so that goes away. So this then becomes the equation if there's not any friction. Whereas if there is friction, then we use the whole equation. Okay, so you see how I got it here? I don't think I want to take the time to go over every single step on it. I mean, it's listed right here. This equation is the one that I got from doing the free body diagrams on the guys on the left side. This one here, I got this equation from doing a free body diagram on the guy on the right. And then I combined them together and did a bunch of algebra. And when I was done, this was the equation that popped out. And from that point on, then it's just plug and chug. So I don't think I need to go through that. Are you guys okay if we move on? So give me so yes in the chat box means yes, it's okay to move on. And if you want me to go through this derivation more slowly, I will, but it looks like most of you are saying it's okay to move on. Okay, good. All right, so it's in the file here. I trust that you've all downloaded the file right now. Okay, so sit down and work through this problem, guys. This is really important. So let me look you in the eye right here while I say this. You do not learn physics by watching me do it. And then you say, oh yeah, that makes sense, I got it. No, the only way to learn physics is you have to do it yourself. So now that you've seen me do it, what you need to do is you need to take the notes that you just took and get rid of them, okay? Start with a clean sheet of paper and do the problem from the beginning, from scratch, without looking at your notes. If you have to pull out the notes and look at them, then that means you got to go back and do it again. I want you to do it from the beginning, from scratch, without looking at your notes, and see if you can get the same answer that I got. So Sam is saying that's paper abuse, Mr. Hendricks. Yeah, sue me. Okay, and so the very last problem here, 22. This is a really good problem. This is basically, remember that extra credit problem that I gave you that very few of you did, by the way. I'm really disappointed at how few of you did that extra credit problem. Shame on you. So anyway, what happened to that paper? I shouldn't have thrown that paper away. Sam, you were right. Let me get another piece of paper. Okay. All right, so let's do this problem from the beginning. Okay, so let me write down the number. I'm going to open up a whiteboard, but before I do, I'm going to write these numbers down. So the velocity is 16 meters per second. The angle of the hill is 5.2 degrees. The coefficient of friction is 0.49. Austin is saying that the extra credit problem isn't on the practice test. Oh, you're talking about this thing on the bottom here? Yeah. Yeah, Austin and everybody else. Yeah, this is something that, oh, this is an old file. The file that's on, the file that I put on Canvas doesn't have problem 23 on it. So ignore this. What you see down here, ignore that. I didn't put that on there. Okay, so, all right, so let's back here. Have I got everything I need to do? Problem number 22 or 20, yeah, 22. Okay, I think I got it. Okay, so let's open up a whiteboard here and let's do this from scratch. Okay, so let's start with the drawing. My favorite problem solving strategy is draw a picture. So here's the hill. Here's the car going down the hill. And it's going at a speed of 16 meters per second, going that way, down the hill. Okay. All right. So we want to know how far the car is going to slide. Okay. So we're looking for delta X. That's what we want to know. And so we say to ourselves, if only I knew what the acceleration rate was, then this would just be a Dr. Seuss problem, and I'm good at Dr. Seuss problems. Okay, so if I knew the acceleration, okay, then I could do this problem. If I knew the acceleration, then I could do this problem. But rats, I don't know the acceleration. So then you say to yourself, okay, what would I have to do in order to figure out the acceleration? Well, what is it that causes acceleration? Forces. So yes, you're right. Sigma F equals MA, right? So it looks to me like I need to analyze the forces that are acting on it. So I've got mg going down. I got the normal force going off like that. I've got friction slowing it down. And I ask myself, which one of these is funky? Well, if it's moving in that direction, then that means that the funky one is mg. All right, so take it down there like that. So this guy is mg cosine. This guy up here is mg sine. Don't need mg anymore. Okay, so sigma f in the x direction equals mass times the acceleration in the x direction. And what forces do we have acting in the x direction? Well, I see a couple. I see this guy here is acting in the x direction, and this guy here is also acting in the x direction. So if we define our plus direction to be the direction the car is moving, that means this guy goes in with a plus sign. So mg sine theta goes in with a plus sign. Force of friction goes in with a minus sign. So that equals MA. Now I'd like to cancel out the m's because the problem doesn't tell us what the mass of the car is. So we're hoping that the mass is going to cancel out, but we can only cancel out the mass if there's an m in every single term. And we don't have an m in this term, or at least it doesn't look like we got an m in that term. Maybe it's there and it's just kind of hidden. So what is the defining equation for force of friction? Force of friction, oops, that's supposed to be an FF. Let me try that again. So force of friction is mu times the normal force. And we're on a hill, so the normal force is not equal to mg. The normal force is equal to mg cos theta. So mu mg cos theta. That's the normal force. All right, so what do we have then? We've got mg sine theta minus the force of friction, which is mu, times mg cosine theta. So that is equal to ma. And now, yes, there is an m in every term, so the m does cancel out. So the acceleration then is just equal to g times the sine of theta minus mu times g times the cosine of theta. Bingo. We know g, we know theta, we know mu. We can figure out a number for the acceleration. Now, that's not the final thing that we're looking for, but that is the intermediate thing that we need to know in order to get the final thing that we're looking for. Okay, so thanks to the work that we just did, we now know that the acceleration is negative 3.89. So now it's just a Dr. Seuss problem. So x initial, let me make that so it's not so fat. So x initial, x final, v initial, v final, a t. So if we define our coordinates such that the origin is where the car was when it started sliding, x initial is going to be 0. X final, we don't know, and in fact, that's what we're looking for. V initial is 16, V final is 0. We didn't know what the acceleration was before, but now we do, negative 3.89. We don't know what time is, so we need an equation that's got an A, it's got an XF in it, but doesn't have a T in it. That sounds to me like it's the VF squared equation. Okay, so then we just do a little bit of algebra. Solve for delta x, stick in the numbers, and bingo, the answer comes out to be 33. Okay. All right, so like I said, ignore this problem down here. I didn't give that one to you. So that's it for the practice test. And yeah, we've got a few minutes left, but not much. Does anybody have any question about anything at all that you want to go over to prepare you for the test? Not hearing any, not seeing any. So that means you guys are going to ace this test, right? I'm sure you will. Okay, so remember that I am going to do the test on Zoom this time around, which is different than last time. So yes, you do need to log into Zoom. You do need to have your camera on, and then I will open up the test, and then everybody will take it while I'm watching you on Zoom. Okay, well, I guess that's it then. You can go ahead and type bye into the chat box. And what I'll do is I'll turn off the recording so that just in case you had a question that you didn't want to ask because you didn't want it to be recorded, then I'll turn off the recording and you can ask it.